Hello and welcome to Fresh Thinking by Snowden Optiro, the podcast where we delve into the technical aspects of the mining industry. My name is Tarrant Elkington, General Manager for Snowden Optiro here in Perth. For today's podcast, we're going to do something a little bit different. It's a bit of a long-form discussion on the area of stochastic mine planning, so an evolving area in the mine planning space, and full of interesting philosophical questions, technical challenges and opportunities for the industry. And so for this podcast, I'll be joined by Matheus Faria from KPI Mining in Montreal. And Matheus is the Director of Technical Services for KPI Mining, who are a company that's trying to deliver stochastic planning to the industry. And so I'm delighted to have Matheus on the podcast. Matheus, welcome to the podcast.
Thank you, Tarrant. It's a nice pleasure to meet with you, to talk about great things that are happening in mining. Thank you so much for the opportunity.
Well, and I thought maybe we could start with a helicopter view, right? So, and this stochastic planning is something that not everybody understands what it actually means. So could you just give us that high level overview of what you understand stochastic mine planning to be?
You're right. Yeah, stochastic, sometimes just this word sounds scary, right? But we're essentially talking about a probabilistic view or a probabilistic approach applied to mine planning, resource modeling, and decision-making process. So essentially, conventionally we are using single inputs for the different parameters, starting from the block models, the assumptions in terms of recoveries, prices, etc. We have a human trend to simplify things and work with a single input for all these parameters. But in the end of the day, we all know that mining is highly uncertain. We never know what we have in the ground. We never know what will happen in terms of market fluctuations. So the best we can do is can we derive different scenarios of what will happen either in the ground, either in the market, either during the operation, and having scenarios from all these parameters. Can we define a production schedule that takes into account all these scenarios altogether? So there are different approaches that can be used to tackle this problem, to mathematically model the stochastic planning algorithms. But here we're going to talk about different attempts were made across the past few years. So there is a very long history of developments in this field, but here we're going to discuss the ones that are more well established, now available to the mining companies through software solutions.
And this space of stochastic mine planning, how did you come into it?
Right. So I'm a mining engineer as a background. Then when I graduated, I started as working as a consultant, mostly focused on operational permits, environmental permits, etc. in Brazil. But then I missed the fun part, which is mine planning. So I wanted to get more involved. And I came to do a master's degree with Professor Roussos Dimitrakopoulos at the Cosmo Stochastic Mine Planning Laboratory at the university. So in there I could get a background on stochastic mine planning and just statistics. And since then I joined KPI Mining, and we are developing the solutions and implementing across different mining companies. So we're encouraging the companies to move away from deterministic approaches, benchmark, test, and gradually adopt the stochastic approach.
And look, I mean, this approach is really new, right? And KPI is sort of has taken on this software, and to my knowledge, the only software that actually attempts to put this into to commercial practice as a normal mode of operation, right?
Yes, yeah, I'd say it's new in the market, right? But in terms of developments, it goes back to a couple of decades ago, right? Mining, if there is something that mining gave to the society, is the statistics, right? And then right away, the simulations methods for mineral deposits, they were developed, right? Stochastic optimization methods were being developed since the 90s. We have already some research done on this field, right? But then technologies evolves, right? And now I think we have computational power, we have more awareness across the industry, we have more experts that are curious to test the solutions, etc.
And so, how did KPI come into taking this sort of position with the trying to take the research into industry?
All right. So the Cosmo Lab and the consortium of mining companies, the board members, they developed this technology within the Cosmo Lab, and then they understood the value. It was tested using different data sets, etc. But they needed a solution that could be used in practice in the industry. So they tried to reach out to other software companies, but it's not simple, right? To put together a whole team to develop a technology that, even though seems very innovative, there's always risk, right? And then KPI Digital, our parent company, and Ben Cohen, our CEO, he was very entrepreneurial, and he understood the business value and how it would bring value to the mining industry, and decided to enter in this competition that happened across different players that wanted to commercialize this IP. And then KPI finally was selected. And since then, we put together a team, consultants, developers, technical support, everything else. KPI Digital already had a track record and optimization and AI and data analytics. So I think it was a very good marriage to combine this background that was initially very focused on supply chain manufacturing, and then combining this background with Cosmos background to put together this technology in the market.
I mean, I think it's really many decades of effort of lots and lots of people, right?
Yeah, so
that have tried lots of different approaches to the problem, knowing that it was important.
yes.
So it's interesting. I mean, a great application to see it getting into industry, right?
Yeah, and that's interesting when we talk to many like optimization experts, mine planning experts, etc. They say, why shouldn't you didn't try this? Why didn't try that? But it was tried, right? So the technology hides many years of research, hides many feedback from the industry experts that contributed during the development roadmap.
So I think we'll probably get to the the how it's gone, because I think that's really interesting. But I think maybe we should take a bit of a step back and talk a little bit about the background of stochastic mine planning, and a bit more of how it's actually applied to start with. So it's probably, and we always, I guess the main way to talk about stochastic mine planning is to talk about the traditional, or to compare it to the traditional method, right? And I think you probably spend your whole days talking about this difference, right? But I guess so the main thing is that we're trying to solve a problem hear that there are limitations in a deterministic mine plan, or a mine plan where we're just using a single input, right? But what do you, from your perspective, what are some of those flaws?
So the flaws that justify the application of the stochastic methods, flaws of the conventional mine planning, starts from the fact that the mining companies are struggling to meet the forecasted tonnages, rates, cash flows, right? So we have many projects, mining projects that failed, right? And they failed by not delivering the economic value or the products that were forecasted, but also projects that surprisingly they delivered much more than what's expected, right? In both cases, we have problems there because we could have made much better decisions if we knew in advance that our mineral deposit had much higher economic potential, right? So delivering lower economic value, it is critical, but also on the other side, it is critical as well. So we have a challenge that the whole mining industry is facing. Doesn't matter the type of minerals, doesn't matter the type of mineralogy. We do our best based on our technologies, the current technologies, to generate more and more accurate production schedules and mine designs, etc. Okay. However, even with the effort, the best efforts we put in place, we're still facing this disconnect between forecasts and actuals, right? And this comes from the inherent uncertainty that we have in the mining field, which is the geological uncertainty. That's we don't know, we'll never know exactly what we have in the ground, right? And the same happens on the market side, that we never know what we have in the ground. So the main drawbacks is, okay, we're doing a plan, we're optimizing things, and then we have the forecast. When we cross this forecast, and even if we cross the resource models against the grade control model, we see differences, right? So that's how we materialize, or we perceive that this uncertainty that's always there, right? So the main limitation of conventional mine planning is we need to go back to the resource models. So we are working with estimation methods that they misrepresent the spatial distribution of grades, material types, etc. Because we have, by construction, we have some limitations in the estimation methods. Doesn't matter how sophisticated they are, but they all smooth out the spatial distribution of any geological attribute. And now we take this model and we're gonna optimize. So any optimizer, doesn't matter how advanced it is, it will now take this model that misrepresents the reality of what we have in the ground, and we're gonna make decisions. We schedule which area should be extracted. And now here are the forecasts that are probably very misleading. And then when we cross again this forecast against the actuals, the difference is there. So, and also we have other limitations there. The most traditional and widely applied optimization methods, they're very sequential, right? So we are making decisions in each step and then propagating these decisions downstream. So, for example, for the open pit, and I really liked the one of the episodes of this podcast about the workflows of open pit mining and underground mining, right? So as we all know, we define pit limits, then the pushbacks, then we optimize the sequence alongside the cutoff grades, alongside the stockpiling policy and blending requirements. But if we select, for example, a bad set of pushbacks, everything else will be highly impacted, right? So we also have, from an optimization standpoint, some limitations that we could improve. And that's why we see in the industry an attempt to have newer software technologies that are trying to combine and optimize all these components in a more holistic or integrated way. And so those are the two main limitations. So the models may be misleading, and then the optimization approach may be also very subjective and cumbersome based on subjective decisions and trials and errors.
And I think I think the industry as a whole, must, I think geologists appreciate how uncertain their models are, right? That models are useful, but they're not perfect. And we're trying to, at exploration stage in particular, or resource, definition stage, the drill holes are very widely spaced, and it's hard to estimate in between, and you end up, I guess coming towards the average grade, right? In some of those estimates by the nature of what you're doing, and which
Yes.
might be fine in some some cases, but also has a lot of variation, and so as you say, it's that variation must have an influence on what the best strategy is for your mind. If you follow on logically, right?
Exactly. Right. If we have a misleading model, for sure, everything else will be highly impacted, right? And in our conversations with resource geologists, they really understand that the uncertainty is there. They really understand the limitations of the methods, and I think they're a bit more open to try stochastic things. While on the mine planning side, we got used, based on years and years of experience, right? We got used to act deterministically. Sometimes we do not question the models, the block models we're working on, right? We don't question, let's say, the block size. We don't question sometimes the approach, how these models ended up being created, right? But depending on the method, the results will be highly impacted. So this has to be.
And I think it's an area that every day or every month I'm more and more interested with this interface between the resource models and mine planning, right? And this is obviously one implication of it, but the value that could be lost, or the risks that could be introduced, or the opportunity that could be lost, by not understanding, the limitations or the purpose of a particular model that a mine planner is receiving. And I remember this from when I started, and you just receive a model and you say, hey, I'm not the resource geologist. You gave me the model. That's where the grade is, right? I'm just gonna design this pit perfectly around that model. And the longer you go on, you realize that that's actually not the case, and that you shouldn't have that blind confidence that the model is trying to estimate globally and locally for you at the same time. So yeah, I think
because at a certain point we're coming up with a long-term production schedule and maybe the medium term, but when we go to the actual operation, we're gonna see huge departures from that plan, right? So the flaws of the conventional approach is actually materialized later on. That's the challenge, right? We're making decisions for the whole life of mine, but the problems will start a couple of years later, right? Once we are actually mining those areas. So that's the challenge, I think, that is slow down a bit the adoption of these technologies, right? We don't see the impacts right away sometimes.
Yeah, no, absolutely. So, maybe we can just go through that process, sort of step by step, how you do stochastic mine planning, and as you say, that the starting point is the model, And so really we're talking about, between deterministic and stochastic, we're talking about the difference between estimation and simulation, right? So you're using your basis for the stochastic planning is conditional simulation, right?
Exactly. So if we can compare, right? Here we're talking about different methods, right? We have many methods for estimating deposits and many methods to simulate deposits. But the conceptual difference is the estimation methods, they will always attempt to come up with a single estimate, calculating weighted averages of the samples we have. And these weights are somehow being derived from varigrams in the most traditional approaches, right? However, since it's an estimation based on averages over averages over averages, we end up smoothing the deposits, right? And the spatial distribution. So when we compare the estimated models against the exploration data that was the basis, we see that the varigrams do not match, right? We see that the histograms do not match. Usually we are underestimating the high grades and the low grades, right? And we are overestimating the medium grade. So globally, we don't have a biased model, but when we look locally, and in particular in the high grade areas, that is where we are as mine planners very interested in, we have there a reduction of the amounts of high grades, and hence we are somehow reducing the economic potential of that mineral deposits. On the other hand, the simulations, we're going to use the same exploration data. And I want you to take these steps back because not everybody understands that there's conceptual differences between the simulations and the estimation paradigm. But we use the same exploration data, we use the same varigrams, the same domains, right? So when we're doing the simulations in practice, it's important consistency between the estimated model and the simulations, because still the companies are comparing, benchmarking the two of them, right? So try to be consistent as much as possible with the assumptions used in the two paradigms. But now, instead of using the varigrams like in the most traditional Gaussian methods to calculate a weighted average, we are now estimating the conditional probability distribution of that block. So now suddenly a block doesn't have a single estimated grade, it has a probability distribution. And here we can see, okay, this block has a higher variability of having, let's say 5% copper, but don't forget it also has a potential to have a much higher grade there because the samples around are showing this, right? Or also this block is it's a higher variability block. It also can be very, very low grade. So now, since this block has a high variability, maybe this block shouldn't be scheduled right away, right? So this comes the sense of risk management. So in the end of the day, not going towards the mine plan yet, as a result, the simulations, since we're deriving this probability distributions and acknowledging the fact that we can have much higher grades and lower grades for those blocks, we end up better reproducing the statistics of the exploration data we have, right? So we look, of course, in the same support, the histograms of the data and the simulations, they should match, or simulations are fluctuating around the statistics of the exploration data. So that's why we believe that the simulations are a more sophisticated way to model deposits, right? And I've seen that the resource geologists, following many conferences related to mineral resource estimation, they really understand these differences. And they're encouraging the companies to use, but now we need to convince the mine planning side, right? So
and I
that's
think
the first.
I think one thing to, that comes to mind, because you say, well, we can't, the simulations better reproduce I guess the grade distribution, which is important, and we'll come, we'll come back to that. And so somebody might logically ask, why can't an estimation reproduce the sample distribution? But the reality is that the simulation is doing all of those good things for you, but the price of it is you don't know where that, yes, where that grade is necessarily in areas where you don't have the data. So each simulation will help to better predict the grade distribution, but its location is unknown, which is a very important part of the stochastic planning process, right? That's
yeah. So yeah, you're mentioning
it's the
things that is
price we
important.
pay for that selectivity, I suppose, is the unknown, that we don't know where it actually
Yeah,
is
but
exactly.
that's the point. Even in highly sampled areas, we'll never know, right? The grades will be still highly unknown. And that's why that's why we do grade control, right? Because then we get more data, and then we're somehow trying to get closer to the reality with the grade control data. So it's not only about better reproducing the spatial distribution of grades, but it's about reporting ranges, right? In an uncertain world like mining, it's important to understand the upsides and downsides you're going to have in terms of ore tonnages, grades above cutoff, etc. Right. So I think that's also the beauty of the simulations, is that they allow us to understand ranges of values. And then someone may argue, okay, that's easy. So let's assume plus 10%, minus 10%, right? And then we have ranges there. But the problem is variability is heterogeneous in the deposit. So we have areas, even in highly sampled areas, we have areas that are highly variable, right? And areas with the lower variability. And unfortunately, very often the higher grade areas, even though they are the high, we have more samples there, they are the areas with higher variability, right? That's what we call a proportional effect in just statistics, right? Areas with a higher mean, right? They have also higher variance, right? So that's why variability is not related with drill hole spacing only, right? It is really related to the geological patterns that we have in the ground.
Yeah,
That's
that's
why
interesting.
that's
And
why it's interesting to report ranges, because suddenly the areas that have higher grades and higher economic potential is the areas that the variability is also highest.
yeah, I mean, that's a very interesting concept, I think, for people to get there, to understand, right? And we know that from, like, even when we look at underground mines, that when it's very high grade, that means that's the highest risk. Not, I mean, high grade is great to have. It's a very good starting point, but it also means there's a much wider variance around what you're likely to get. The same thing when you're trying to high grade or grade stream, in an open pit mine, that when you're trying to mine that the highest distribution, that's when your uncertainty is the highest.
Yes, and that's why intuitively I've seen some like underground mine planning being done, in which we downgrade a bit the very high grade stopes, right? Because intuitively, some mine planners would understand, okay, that it's very high grade, the risk there is maybe higher, and then they downgrade a bit those stopes, right? But again, that's why there's the beauty of the simulations, because this will give you ranges and show you especially areas that you have higher variability, And as a byproduct, you can also make decisions based on this uncertainty and variability, right? In areas that you're seeing a lot of variability, maybe you should target those areas for additional drilling, right? So here we're touching a very important thing that stochastic approaches enable us is like decision making under uncertainty, right? By understanding ranges, understanding probabilities, we can now have a more informed decision making process as opposed to blindly trusting in a single number.
Absolutely. And just one, I don't want to go too deep into this topic because I mean, you sound more like a geostatistician than I ever will, but but we're touching on other people's turf here. But one of the great advances, and I know that you guys are thinking about it as well, and when we went to at the MRE conference, it's a big theme is estimating or simulating the uncertainty in geology, and not just in grades, because I mean you talked before and you say like we keep things similar, right? We keep the domains the same between the estimation and the simulation, but that's not always that's the base case, but the potential is that we have uncertainty in our domains themselves, or which introduces a further important
I just
step.
want to emphasize that when I said that we're keeping the same domains for consistency, I don't mean necessarily the boundaries or the contacts between the domains, but the samples that are considered as being part of our domain. Because you're right, absolutely, we can simulations. The uncertainty is not about the grade distribution, but also the contexts between different mineralization zones, rock types, weathering phases, etc. Right? And then we can simulate these contexts and assess also the volumetric uncertainty. That is really important, for example, for underground mining, right? It is much more selective extraction. So measuring and modeling that the volumetric uncertainty is very important.
Because I think when somebody is doing an estimate, that's the other part of a deterministic mine plan or estimate, is that a deterministic interpretation of the geology, and that is where probably the greatest uncertainty lies. Once you have your domains, the estimation or whatnot is or simulation is fairly well known, right? But where the ore body goes in areas where you don't have data, the tonnage, is really important, or causes a much more variance, which brings this to light. And when you do look at simulation results, which vary by simulation versus an estimated lithology, you see it comes to terms with the fact that the resource estimator is making a deterministic decision, a binary decision, 1 or 0, whether this area connects or does not connect, and if it does connect, might find its way into your mine plan and nothing be there. Or they might think, no, we don't think it's going to be there, so it gets excluded, never mind, never considered for your mine plan. Right, and reality is somewhere in between. We don't know until we drill. So how do we get a balanced view of that situation in our mine planning, I guess?
Yeah, so that's why when we simulate contacts, right, between different mineralization domains or lithotypes, etc., we can now, looking at the simulations, derive like probability maps, right? And then you're gonna see that the contact between two categories is in some areas very fuzzy, right? Because you have a high uncertainty in that area or higher variability in that area. In other areas, though, the contacts are not that fuzzy. The probability maps are showing that you don't have a lot of variability there, right? So this is an important characteristics that the simulations enable us to see, right? And variability in the context as well. Yeah.
No, I mean, I think it's definitely a fascinating area, but maybe we should move on to the next the next step in the process. So once we've got the simulations, right? So what do you typically do with you know, what does KPI typically do in going through a stochastic mine plan from the point of having those simulations done?
Okay, so you want to talk about once the simulations are available or before the simulations are available?
When they're available.
Okay, so once the simulations are available, usually we follow two paths in parallel, right? We can use the simulations to do risk quantification or risk analysis, right, of the deterministic schedules that are being generated at the companies, right? This is a very important step, but to understand the limitations of the conventional mine planning framework. It's a very important step for us to better understand which areas are more critical or riskier within our deposits, right? It's interesting to understand which targets are critical and have a higher risk of not being met, right? So we do this whole study with the companies to understand risk and start thinking in a probabilistic way. What are the chances or probabilities of meeting the ore tonnages or feeding the mill, right? What are the probabilities of meeting the product specs? So we do this work, right? Risk quantification can be done in any software. So it's not about the software, it's about methodology, right? Of course, in our software, we can build the economic model of the whole mining complex and then do the risk analysis by leveraging the simulations and comparing that against the deterministic sequence of extraction and cutoff grades. So that's the first study, but it's very important and prepares it's the foundation for
like a baseline. Yeah,
it's a baseline, exactly. And it's important as well to have apples to apples comparison against the stochastic results, because again, even though the models tend to be very consistent, differences will happen because the simulations and the estimation methods, they have some differences. So once the risk analysis is performed, then we start doing the stochastic optimization of a long-term production scheduling. It's important to highlight that today the technology is focused on long-term planning in open pit, right? We can talk about later about underground mining as well, but that's our focus today. So we're gonna start building the stochastic optimization of the long-term production schedule. So then we follow all the same, we always have a benchmark, right? So we follow the same economic operational assumptions, right? We build the business model, and then we do the optimization, we go through the optimization, we compare results, right? And then based on the results we had, plus the risk analysis, right? That's how we do an apples to apples comparison. And we're going to understand that, yes, if we look at the deterministic schedule, your risk is higher than if you follow the simulations, right? But now, both models are models. The simulations are a model, they're not a reality. The estimated models model is also model, it's not the reality. Which one is the actual one, right? Yeah. So that's why from an adoption standpoint, we compare the deterministic versus the risk analysis of the deterministic versus the stochastic, but in companies that are in mines that are already in operation, we have now grade control data, and we can now compare the forecasts against the grade control model, right? And this additional comparison is what is giving the companies a comfort level to switch or to try more and to scale the stochastic mine planning studies, right? Is this comparison against the actuals, right? In the end, that's how I think it's the turning point. Once we have this data available, right? The grade control. Of course, this is only possible for mines that are under operation, but my analogy in mines that are for exploration projects, right? We are positioning that, okay, based on these studies that were done for operating mines, we're confident that the feasibility studies, economic evaluation can be much more accurate for exploration projects as well.
And so for those, I mean, I think that's a good approach. I mean, it's a very good question, like which is, and we see that sometimes the difference of grade distribution can make a big difference to the value of your mine. But you know, to compare back to the grade control is interesting. What's the you know, and what have you found with that? You know, how do the grade control compare against the simulations or the estimation?
Right. So it's important to highlight that when we do this comparison, right, we need to make sure that we treat the grade control data to eliminate any bias that usually grade control has, right? The quality of the samples is not the same. The support of the samples is not the same. So we need to do some corrections. But having done that, right, these comparisons are showing very interesting things, right? From a contacts standpoint that you mentioned before, right? So the simulations, so we have interesting cases in iron ore deposits, right? The companies that were struggling with some occurrence, unexpected occurrences of waste in the middle of ore packages, right? If we look at the resource model, based on the exploration data, we would assume that this is a big ore package, right? The simulations, on the other hand, even though they were based on exploration data only, they were saying, no, be careful, this area, we do have a probability of having waste zones here, right? And then when we looked at the grade control, we could actually confirm that the simulations, they were advancing this probability, and was confirmed by the block model, or by the grade control data, right? In terms of grade distribution, also we've seen comparison, right, that some areas that were very high grade in the estimated model, right? The simulations were showing, no, this area is probably lower grade, right? So you have an overly optimistic forecast for this area in this production period. And then the grade control data has confirmed that the downgrading of that area, right? So I think that's interesting findings, right, that were shown. Of course, simulations will also suffer for data data availability,
Scarcity.
right?
Yeah.
If we have a very poorly sampled data, the simulations is not a miracle, right? It's a model again, right? But for the areas that we have more confidence, even measured resources areas, right? We are seeing that the comparison with grade control data are somehow confirming what the simulations have anticipated, right? In terms of, oh, there is a probability of this happening here. So that's a very interesting finding that encourages us a lot.
Yeah. I think I mean, it's just such a fundamental thing of understanding, right? This whole piece. Of course, the simulations can't tell you exactly where the data will be, but does it look more like the grade control? And I guess if we step back to some of the methodology, maybe I could just ask, with the simulations, obviously we're sort of estimating initially at like at a point support or whatever, right? You're doing things to those simulations to convert them to a mineable distribution, right? So what sorts of things do you do to the simulations to try to reflect the selective mining unit or whatever?
Right. So it depends on which software or algorithm
Sure.
you're using. There are softwares that can already deliver simulations in SMU scale and block
Yep.
support, right?
Yep.
But the most traditional way is with simulating point support, right? That's where we can properly validate and compare the statistics against the statistics of the simulations
Yep.
against the exploration data, because they're in the same support, and then we scale, we reblock the simulations to the block support, right? Because in the end of the day, we need to do mine planning based on SMU size. So that's how we are handling this change of support, and it's interesting, right? Because we're somehow accounting for dilution, right, in that approach, right? Because we can have we can have points showing that you are part of another category or waste, for example, and then when we reblock, you're going to have the dilution being somehow brought to the SMU size, right? The same the ore loss, right? So it's very interesting, this change of support. Of course, needs to be properly aligned with the mine planning team, right? Yeah.
That's excellent.
I
And
don't know if I
then,
answered your
yeah,
question.
no, you did. I mean, I think it's like an estimate or like a Krieged estimate, which is actually at a much different point support. A mining engineer will typically do the same thing or reblock it or whatever. But at very different starting points between the two models. And I suspect, this is just my opinion, and it probably varies from very much varies from deposit to deposit, but like an ordinary Krieg estimate, particularly for a bulk, deposit, has a lot of, but through its averaging or smoothing, actually does dilute, effectively mimic the diluting process, potentially over diluting, the deposit and missing or non-identifying areas where it could be higher grades or lower grades. I mean, that's the fundamental part of it. And again, it comes back to which is the most appropriate way. I mean, you think that through the simulations, they probably need more dilution added to them than an ordinary Krieged estimate would. So it's, but it's the devil is in the detail and reality, right? The other thing I was just going to ask about is so when you talk about doing an optimization, you're implying before that, like we prepare the models for optimization. Now, typically in deterministic scheduling, and that's maybe changing now with direct block scheduling, but we do a pit optimization with that. And so within your software, you're saying that we prepare the simulations. They're just multiple versions of the same of a model or of grades that go into an optimization, which is a direct block scheduling algorithm, right?
Exactly.
It might just be
Yeah.
worth just highlighting very quickly what direct block scheduling is.
Okay, all right. So just to clarify, right, the phase bench, the traditional phase bench approach, could also work stochastically, right? We could have a phase bench approach with a predetermined phases, pit limits, and mining panels based on the simulations. That could work, right? However, again, we are making decisions, we're constraining the scheduling by having predetermined phases and predetermined pit limits that were generated by not taking into account the NPV directly, right? Once we select our final pit limit based on a revenue factor, right? This selection is subjective, right? And the revenue factors do not account for NPV, right? We do have a base case and a worst case scenario. Companies, they have different rationale to select where is the pit limit. But again, since the 60s, right, we have this concept that the schedule should drive everything else. The schedule should drive pit limits. The schedule should drive the phases. The schedule should drive the cutoff grade policy, right? But at that time, we didn't have computational limitation, computational power to handle the scheduling problem directly at a block support. So the best we could do at the time was let's break the problem into smaller problems. And that's how the pit limit optimization came out, right? The definitions of pushbacks, or in Australia, cutbacks, came out, right? Because then we can now have a scheduling problem that can be handled by the computers we had at that time. So the direct block scheduling approach that we have in our solution and in others as well, right? It's now trying to have this, to really satisfy this concept that the schedule should drive everything else. So here we're actually iterating over the year of extraction of each block, right? And now that we have a sequence of extraction for each block, we know which year each block will be mined, and now we can go back and group periods to generate phases, and where the schedule decided to stop mining, that's your scheduling driven pit limit. Now, a point that many people argue is, okay, we cannot mine with a helicopter, right? We need to account for sink rates. We need to account for mining width, right? We need to have mineable shapes, right? And that's why we need to integrate this mineability constraints, that's how we're calling it, into the direct block scheduling approach, right? So we are now saying, okay, in order to mine this block, you need to mine a whole neighbor, right? A whole mining width window around that block, right? For this block to be considered. And that's how we can generate mineable shapes in the end, right? That can be now fed to the mine designing approach. So we're kind of switching, the direct block scheduling switches the conventional mine planning workflow for open pit mining, right? Because we spend a lot of time in the early stages doing the mine designs, right? As soon as we have the grouping of pit shells, we do the mine design to schedule within these mineable shapes, which does have the very straightforward advantage that the shapes are already mineable. But on the other hand, but here we are doing the other way around, right? We have already a mathematical schedule that does generate mineable shapes, and now we do the design later on, right? Of course, whenever we do the design, we are adding waste blocks and losing some ore blocks, right? So we need maybe to reevaluate the schedule after the designs, but the bottom line is that the phases now, since they're coming from a grouping of periods, we make sure that those volumes, they do satisfy blending requirements on a yearly basis. They do satisfy all the physical constraints, right? You cannot advance in this area up to year 5. So we are generating here a phase that skips that area. So we have now phases that account for the time, accounted for the time dimension, right? So that's a much more interesting way of deriving the mine design, right? And again, phases that were generated in order to maximize the NPV as opposed to in order to maximize the undiscounted value. That's how the pit shells are meant, right? So that these are the main concepts of direct block scheduling that are giving, even in the deterministic area, right, are giving interesting insights for the companies to define phases, right? We have deposits that suffer from gap problems, right? That suddenly the value explodes, right? When we change slightly the revenue factor. And so the direct block scheduling is also adding value in that front, right? Generating phases that are more profitable because they account for NPV directly. But now the point is, okay, direct block scheduling, what is the link with the simulations, right? And
Good question.
that's a good marriage, right? Because okay, as we discussed before, the simulations better represent how the high grades are, right? Spatially distributed, right? The scheduling part, on the other hand, are saying how many waste blocks I need to mine all the way to reach out to a high grade block that will pay for everything else, right? So now having models, resource models that better represent the spatial distribution with a direct block scheduling approach, well, that's where we can unlock a lot of value.
And I guess that's where you can directly, I suppose, without the pun, understand the difference of the balance that you're getting from the multiple realizations on on your schedules, right?
Exactly. And now it comes to the objective function, right, of the model, right? So we're not only attempting to maximize the NPV, looking at all the scenarios and all the simulated rates, but we have another component in the objective function that is now trying to minimize the risk, right? So which means that for all the scenarios that are being used, right? Can we meet the ore tonnage targets? Can we meet all the grade specs, etc.? So this balance that you mentioned, that is interesting here, right? It's only possible with the deterministic with the stochastic approach, because deterministically it's easy to meet all the targets because you only have a model, you're constraining your sequence to meet all those targets. But now having 20, 50 block models, 400 block models, can we meet these targets, right? For all the scenarios, like as an ensemble. So that's where it comes the risk minimization component that exists in the objective function.
And that objective function, which for deterministic might just be net present value, obviously you've got multiple versions of reality. So the basis for that objective function, I mean, you talk about sort of adjusting it for risk, but you're looking at generally the average NPV of all realization of the schedule for all realizations, right? That's the
yes. So we are accounting for the average over all the scenarios, right?
Yeah.
For the NPV, right? Maximization, but also the average of this risk management component, right? So which means that for every single scenario, the model attempts to minimize deviations from targets. So in doing so, we are driving the sequence to avoid riskier areas, right? So here in areas that would generate a high risk, that area is avoided in the optimization process, right? So that's why it's a balance, because maybe you would have an area with a very high economic potential, but it's a very risky area. So the other component would delay that area to later on.
Yeah, and I think I like how I often think of the mine. You know, people often talk about the mining decision, right? And the direct block scheduling is a very good way of describing that. So you've got a block and it's got value, and you really the decision comes down to, do I mine this? You know, where do I send it, and when do I send it? And so, you know, when we think about what the stochastic planning might do, it's interesting to think about the implications it might have for that decision, right? And so if I start with the pit limits, right, and if you think implicitly, you know, one thing I always have in my mind is that like to tell mining engineers to look at the drill holes, because every traditional pit optimization that you do, every nested shell you get, is always trying to get to generally a high value block or set of blocks in your model, to drive on that, as if it's very, you know, certain that it's there. So one thing I would encourage anybody to do, and I tell people a lot, is to go bring the drill holes in and see what is actually supporting that area that you're driving on. And the second part is to make sure that you get at least enough of that so that you don't miss it. Because, you know, I think there's a great chance that people plan on a very deterministic model and the high grade ends up in the wall, right? Whereas a simulation approach would give you, I always think in my mind, like a balanced view of of the possibilities, right? So there's a penalty for that, right? Because you might need to mine more to give yourself the certainty that you would get that high grade area, right? And the price for that, you might have to drill it more. Like if you want to reduce that down, you might go and, you know, drill it and become more certain about where that pushback should be. But
and there is another component, right? A limitation of, let's say, pit limits, deterministic pit limit algorithms. They're based on economic value of blocks. If we're talking about economic value of blocks, right, predetermining the destination of that block, right? Because we're gonna have a waste and poor blocks with negative and positive values, right? But in reality, what is ore, what is waste is the blocks are never processed separately, right? The blend of a low grade block with a high grade block that needs to be economic. More than that, right? It's not only about the blend, the economic value per se. This blend needs also to meet all the targets for contaminants, all the targets for all the grade specs and any other metrics, right, to define a product. So that's why the direct block scheduling approach and the stochastic model enable us to model directly the values of the blended materials in the end of our mining complex, right? So now we're assessing, okay, I want to extract this block in year one. Based on the simulations, this block can be ore, and it will be evaluated as ore. It can be wasting, let's say, 3 out of 20 scenarios. So it will be evaluated as waste as well, right? So, but we are doing this evaluation on when to extract the block based on the value it will bring in the end of the chain, right? So that's another interesting aspect, that just advancing a concept that a topic that you bring up, right? For deposits that are highly driven by the blending, right? It's a better approach because we are defining the pit limits, the phases, and the scheduling, accounting for what will happen in the end, in the blended materials, as opposed to blindly or directly looking at the economic value of blocks in isolation.
Yeah, I think it's a great point, and one, when we think of that, when we're talking about simulation versus estimation before, and we're generally thinking about that in terms of a precious or base metals project where there's a single grade and you're trying to maximize it, right? Rather than necessarily a blended grade. So that change in grade distribution might be very favorable for us to be able to isolate the high grades. But in a in a blended situation, we also see the same thing too, that an estimate will smooth the grades, bring them more to the center, and potentially give you the false impression that it's easy to blend this deposit because there's less variability showing in the model, whereas in simulation it will show more extreme values, and those extreme values make it difficult if you get stuck in a pod of low or high to blend. So the blend equation or strategy completely, the simulations both expose a problem, you know, to you, but also interesting ways of being able to resolve that, I guess.
Yeah, so because we're essentially underestimating the contaminants, right, that are also a very important part in the blending, right? So we are having probably a more optimistic vision if we solely look at the estimated models, right, to define the blending strategy. And that's another use case that we have for deposits that are highly driven by the blending, right? The simulations gives you a different strategy, right? So we're mining different areas because we're attempting to minimize the risk related to blending as well.
And I guess I've always been curious about this as to, think about financial theory and diversification of stocks and things like that to minimize your risk, things that are less correlated. And so in your experience, do you see that happening? So when you try to reduce the risk, you maybe mine more areas, simultaneously because those areas might not be so correlated, right? So rather than focusing all on one area, maybe in a deterministic, you say, well, the high grades here, okay, we're all going to go all in there. You might maybe need to have another cutback operating to diversify some of that risk.
Exactly. So yes, it can happen for some deposits that are now, instead of having a more concise extraction, we're kind of opening more fronts to have the flexibility to end to manage the blending requirements, right? But as long as these shapes are mineable and economic, right, and leading you to the same NPV or even higher NPV, this strategy is showing that it's possible, right, from an economic and operational standpoint.
So I think maybe it's probably worth us, talking about some of the basic the principles of stochastic mine planning. So some of the things, and we kind of touched on them, already. I think we've gone through quite a few of them, but I think one that's very important is that we are making, and this is where sometimes the concept of real options comes up, is that by we're assuming that you're going to be doing grade control drilling in the future to get more information about the deposit in the future, right? So that's where some of this value, is coming from, is that look ahead or possible look ahead to the future, right?
Yeah, exactly. So that's some people will say, we don't need to overly complicate things because in the end of the day, we're going to do grade control, right? But you do grade control in the areas that we're already extracting and based on your deterministic approach, right? If you were to follow a stochastic approach, you probably would be following a different extraction, right? Mining completely different areas, and then your grade control would be completely different as well, right? So it's this look ahead that you mentioned that is very important.
Yeah, and I think when we talk about looking ahead, one of the very important principles of stochastic planning is that we're not cheating, right? We're not, and it probably ties into the question of can't we just why, like we've got all these simulations and lots of people, want it's very appealing, and they say, well, I've got 20 simulation realizations, I'll just go and run a mine plan on each of them, And,
yeah, so that's again, this is a misunderstanding that some people have, right? Because, and this may prevent the adoption, this misunderstanding, right? Because people may, okay, you were working with multiple block models, now need to do multiple production schedules, right? And then which one I should follow, right? And that's not how the process works, right? We're not defining a plan per simulation, right? Because if we do so, we never have a final schedule and mine design that can be followed in practice. The concept that we have here is, can we generate a single sequence, right? And a single cutoff grade policy that looking at all scenarios at the same time, and that will enable us to minimize the risks related to the production targets. So it is a schedule that will not be the optimal one for scenario 1, will not be the optimal one for scenario 2, but will be the best for the combination of scenario 1 and 2 together, right? So, and this is possible because in the model we have decisions that are looking at all the scenarios at the same time, so we don't diverge from one scenario to another, and decisions that are taking scenario by scenario. So the impact for one scenario, if that block is ore, right, it will be evaluated as ore. If it's waste, it will be evaluated as waste, right? And okay, many people may argue, but you need to know the destination of the block. How come you're not setting that block is ore or waste? But this is mimicking what happens in reality, because the final destination of a block is only determined once we have grade control and we are about to load that block that was blasted, right? But in the long-term planning, the best we can do is assessing all the possibilities, right? But we want to assess all these possibilities, and in the end of the day, generating a single plan that can be followed in doing the operation, that can feed the mine designing process. So that's the conceptual idea of the stochastic model we have under the hood.
And in reality, we could always, there's even abilities to improve it, because in reality you get more information as you evolve, and the sequence can change. So
yes.
So at the moment, and that sort of is another dimension to it, but it's picking a sequence and you're sticking to that sequence through all these realizations, rather than and allowing the destination to update based off of a policy, right?
Yeah, and you're bringing up a very interesting point, right? That is said, in the future we're going to have additional information, right? Our knowledge about the deposit will evolve and the sequence will probably change. That's right. But that's why in that risk management component, we are discounting this risk over the life of mine. So which means that I want to be very certain in the early periods, right? Because that's the data I have to date, right?
Yep.
And we're deferring the riskier areas to later periods under this assumption that our knowledge will evolve, right? And the sequence is dynamically changing, right? Whenever we redo the planning cycle.
So it's effectively exactly the same issue that we deal with in deterministic in a different way, right? But it's a great point, that continued focus on the next 5 years is the most important, right? The rest gets blurrier and blurrier, but that's okay,
yes,
for us.
Yes.
Yeah.
But because again, it's understanding that the earlier cash flows are the most important ones, right? And these earlier cash flows should derive the phases, should derive the strategy, right? For earlier cash flows maximization, but also that at the end of the day, we want that those higher earlier cash flows are also more reliable. So that's the point.
And it's great because it's a single plan. At the end of the day, you've got to do something, right? That's the reality. I think there are a couple of use cases for running an optimization on a single realization, not for production forecasting per se, but if you did run an optimization on a single realization, it might tell you what would be the benefit of drilling your entire deposit to a grade control scale before mining, right? So if you wanted to realize the whole benefit of a single realization, you could drill the whole model out and then estimate it, and the simulations and estimations might be the same, but does that actually worth doing? That's probably not going to give you that much extra value for the drilling that you would need to do for it. And the second thing in my mind is by running them separately, you can identify where each one would be most different, which might give you a good place to drill that would have the biggest impact, not necessarily on classification or whatever, but on your mine plan, which is ultimately what a resource estimate is going to be used for, right? So if one if there's an area of the mine that in some realizations would be mined in year 2 and in other realizations in year 7, then maybe that's a good place to drill, because that's a source of variance for the model. So there are some applications. They're not things that should be used for your production forecast or valuation, but might help guide other parts of your business.
Yeah, like where we should place some infrastructures, right? So analyzing scenarios separately wouldn't give value, because then see the maximum extent of your pit. So there are, right? And also this approach is what is being somehow used for drill hole optimization approaches. That is another use case that the simulations are used, right, besides mine plan. So that we're essentially generating scenarios of based on different drilling patterns, and then we evaluate that based on the simulations.
But I guess, like if you were to put the hat on of saying, that drill hole spacing optimization purely based off of the geostatistics, right? That's one thing, but ultimately we're using this for a mine plan. So if you were to go into your stochastic schedule and identify the areas of greatest variance in your schedule, then that might give you a better, application for your drill hole optimization for an economic outcome, right? Rather than a classification outcome.
Yeah, because in the end of the day, we need to classify areas or define where to drill next based on extraction volumes, right? So you need to have your yearly panels or your quarterly panels. And this should not be defined arbitrarily by just reblocking things. The mine planning ultimately should give you this grouping of blocks, right, that should be extracted. So that's an interesting thing. And again, when you do the stochastic production scheduling optimization, you can now see the risk profiles, and you're gonna see that this area has a higher spread, right, or between a higher gap between the P10 and P90, right? And this area is probably where you should also tackle as the next target area for additional drilling. And again, based on a volume like for a year.
Yeah. So I mean, I think there's a lot of use cases, right? And I think we've probably covered all of the main guiding principles, I guess, of stochastic planning, unless I've forgotten some.
Yeah, like I just would like to emphasize the cutoff grade optimization, right? We still see many companies that are not optimizing cutoffs. They're still relying on fixed break-even cutoff grade policy, right? And we know that optimizing cutoff grades can unlock substantial value for any operation, right? So now, can we optimize cutoff grades based on the simulations? So what happens behind the scenes here is that the algorithms, they iterate over the cutoffs, right, for each period, right? But now, so we are delivering in the end of the day a single cutoff grade policy, looking at all scenarios at the same time, because we need a guidance, an operational guidance. So for this year, this is the cutoff, right? But now the block will be evaluated. If it's a block with a higher variability, this block will fall, let's say 10 out of 20 scenarios as a OR, and it will be evaluated as OR. And in 10 out of 20 scenarios, it will be evaluated as waste, because ranges of values is covering both sides of the optimized policy. But now, if your block has a lower variability, it will be consistently sent to one destination or another destination, right? But so that's the mechanism that allow us to have probabilistic forecasts, even though we are still based on a single policy that can be followed in practice, right? So that's one of the mechanisms. So besides the DBS, the direct block scheduling mechanism that we discussed before, we have this embedded cutoff rate optimization that will adjust for the different material types. We'll adjust the cutoff year after year in order to meet the targets.
Like an embedded option to process each block, which is what you have in reality, as you say.
Yeah, so we have that policy, right? It's not a policy per block, right? It's a policy per year. So for that year, the cutoff should be here, right? Now the destination of the block will vary according to the simulated grades, right? Block by block.
That's excellent. I think. I mean, I think that's a very important part of the process as well, mimicking reality. Just talking of reality, I guess maybe we could talk a little bit to how it's gone so far. You know, now I think you took the software on how long you know, you've been testing this software in, let's say, in commercial practice for.
Okay, in commercial practice, we launched the KPI mining in January 2023, right? And since then, we are testing different types of minerals, right? We're testing it in different types of mineral deposits, different scales, right? So we are now much more confident in terms of scalability of these methods, because again, it's computationally intensive, right? And we're having very interesting and successful cases. So for sure, we have interesting projects done on gold deposits, copper deposits, and multi-metal deposits, copper, gold, copper, silver, copper, zinc, moly. So we have different very successful use cases for these precious metals and base metals, right? But also we have very interesting successful cases with iron ore, right? And I like to bring up iron ore because I heard many times iron ore is highly homogeneous. We shouldn't complicate things, right? But it can be homogeneous if we look at the iron grades. However, the deposits are shown to be highly heterogeneous when it comes to contaminant grades, right? When it comes to the hardness of the rocks, comes to the different ore types, right? And that's how we're also adding value to these types of deposits that are highly driven by the blending, right? So we have also interesting cases for nickel laterite, nickel cobalt, etc. So we want to also have more successful cases for phosphate mines, right? For bauxites. This we still don't have many successful cases, but it doesn't mean that the methodology cannot be applied to these deposits, right? It's just because these other commodities, I think they are they're run by large organizations that can invest a lot in new
Yeah,
technologies.
that's what I was gonna ask. I mean, is it typically the larger companies that are trialing this, that are looking to implement this initially, right?
Yes, for two reasons, right? First, they have bigger teams. We never expect that the companies will, from one day to another, change the whole approach that they're doing for years and years and switch to stochastic. So you need to have the spare capacity in your team to test, to benchmark, etc. So, and larger companies, they have this possibility, right? They are not maybe short-staffed in both teams, mine planning and resource modeling, right? Because we need to engage. It's an end-to-end engagement, right? We need to engage the resource modeling teams to generate the simulations, but also because usually we have very experienced geostatisticians and mine planners in these larger companies as well. So it's a more diverse teams, right? More multidisciplinary teams. So I think the environment. But we had interesting cases for smaller companies as well, right? It depends on the challenges that they're facing and the urgency to fix these challenges.
And so these cases that you do you does KPI do them internally, or do you do them as part of internal, a team with the clients, or?
It depends on the stage, right? Usually we start doing the studies internally because in our adoption journey, we start based on a POV, right? A proof of value project. It's a smaller project. We target a smaller mine or a simplified case that we still have a benchmark available. So then we may do that internally just because the teams are already busy doing their regular mine planning workflows. So then once this value is proven, then we scale that. And then we really do a software implementation approach by training and holding the hands of the teams to be able to implement that internally, right? And adapt and simulate that stochastic process as part of their workflow. And again, the companies are still using the stochastic in parallel, right? It's a lot of benchmarking going on. They're still reporting based on the deterministic side, but they have their business case based on the stochastic side. But we believe that at a certain point things will start migrating, shifting towards stochastic as they become more and more mature and confident about the method, right? It's all a matter of confidence, right? We used to do mine planning in spreadsheets, right? The industry needed to, at a certain point, to start testing lash grows and start testing more computer-based optimization models, right? And now the same process is happening here.
And I think in concept, the software to do stochastic planning itself is not really like, if you were to think as a mining engineer, what do I need to do to change? The answer, I'm guessing the answer is probably not much. The inputs are very, very similar. You're just the main complication, I guess, would be generating the inputs, which is in the realms of the geologists, and then interpreting the outputs, right? Because there's obviously more richer information that comes in the outputs. Is that a fair?
Well, of course, a background in these methods, it is an important blocker, right? In very few mining engineering programs at the universities cover this technology. So the mining engineers would need to, at a certain point, study that, right? But what you're saying is absolutely right? It doesn't change a lot, right? It's not simple to change the mindset to work probabilistically, but somehow we're doing that already, right? When we do sensitivity analysis, in the end of the day, we want to understand ranges, right? We want to understand probabilities and risks, right? But now we're doing that, deriving these probabilities based on the simulations.
And I think one thing that I mean, I'm curious about, and when you talk about ranges, and so when I'm in Australia, and we have JORC, and you look at the JORC tables when you put out resources and reserves, and they talk to a range, reporting a range or uncertainty on these things, and typically people don't do it. That they'll imply that it is captured in classification, but simulation and this approach with the probabilistic outputs does give a path to that. And I've always thought that I guess the challenge for stochastic mine planning to become more mainstream in its adoption is to be able to utilize the simulations for reporting resources, which is not typically done. There's a couple of applications that I've seen in recent times, but very, very rare. And I know Clayton, the recent MRE conference, Clayton Deutsch was sort of proposing this, and I think it's an important step. I mean, where do you see this work, falling into the workflow of that governance structure or compliance structure in resources and reserves?
So a couple of years ago, I asked for some CRISCO members, right? Because they said we need to report ranges. We need to report the level of confidence. And I say, can we change the codes to promote the stochastic methods? The answer I got is no. We don't need that because it's already in there. Just people are not doing. It is in there that we need to report ranges of values. We need to report confidence, right? And we are usually reporting confidence only based on the drill hole spacing. And as we discussed at the beginning of our talk, that variability is not only driven by the drill hole spacing. It is related to the inherent geological phenomena, right? So it is in there. The codes, they don't prevent the experts to use one method or another. The codes do not tell you to use deterministic methods only, right? They don't tell you to use kriging. And that's why we still see some reports that are using inverse distance, right? Even though we know that it's not the most sophisticated method, right? So it's all the matter of a confidence of the experts, the CPs, the QPs, as soon as they are more familiarized with the methods and with the software, right? Because in the end of the day, we need tools. The methodology is something, right? But we need tools to generate the simulations in a very performant way, tools to perform mine planning in a very performant way, right? The stochastic mine planning in a very performant way, tools to generate risk analysis, right? In a very efficient way. So once this is more well established, and once they have this comfort level, I think it's a natural path evolution that will happen in the industry, right? So that's why we're pushing hard. We're starting with some larger companies because historically they are more innovative, and also with we're partnering with the consulting firms, large consulting firms, just like Snowden, right? That have this credibility that things can be tested, credibility and curiosity, right, to test new approaches, methodologies, etc. So I think from a regulatory standpoint, it is already there. We have all what is needed. What we need is awareness in the ecosystem, right? And so the experts needs to be more trained, more aware, and have the hands-on on these methodologies.
Yeah, I think it's a good term you used, is the like the ecosystem of it all, because it's about and something that I'm quite passionate about. So mining engineers understanding a bit about resource estimation, and resource estimators understanding a bit about mine planning, because that's always the discussion. Why generate simulations if they're not going to get used by the mining engineers? So I won't bother. Oh, I can't do stochastic mine planning because I don't have any simulations, or I don't understand, or these sorts of things. So I think it's a big educational, exercise to reduce the fear or of uncertainty that people have about these things. I mean, do you see a world where we only do stochastic, mine planning? I mean, it's a bit.
Yes, I hope. So we need to, I think, to get inspired by the oil and gas industry, right? They are employing stochastic approaches for decades because they understand uncertainty and variability very well, right? Their sampling is much sparser than ours in our case, right? And also they have the characteristic of the reservoirs change over time, right? And when we're extracting the porosity, the permeability will change. It's not like us that we are extracting the block, so the geology doesn't change in the ground, right? What changes is our understanding about that block. So I do see a world where the stochastic would be widely used and become a standard. We're not there yet, right? I think it's a gradual process, right? We didn't have computational power and models that could leverage the simulations. Now we have, right? So now it is the big opportunity that the companies have to start testing and implementing that internally. So we had like a logical blockers before that now are becoming more available to the industry. And this is happening not like the rate that new technologies are arriving to the mining industry is very fast right now. So it's not only stochastic mine planning, right? Other technologies are also being tested and experienced by the company. So yeah. I think it's a natural path.
It'll be interesting to see. Maybe if we could just change tact a little bit, and I know it's not something that's in the software at the moment, but an area of your I guess from your masters and so I suppose an area of your interest in underground, also stochastic planning for underground. And maybe we've focused a lot on open pit, but maybe we can just highlight the application of stochastic mine planning potential for underground.
Exactly. I think my research was based on underground mine, right? I also like a lot to talk with the Chris Alford, right? He's also a very enthusiast of this topic, right? So applying stochastic methods to underground mining. And I see a lot of potential. Why? Because, again, the mining methods are much more selective, right? And hence, I think the variability plays an even more important role in underground mining, right? And here it's not about how the grades are, how is the grade distribution, right? Is how they are connected to form stopes, right? So you can do this testing, right? You can do stope optimization in different realizations, okay? Not necessarily the scenario with the higher inventory of a metal will be the scenario with the highest metal content within the stope design.
Okay.
So there is this asymmetric relationship between metal content in the resource model, in the simulation, and the metal content that it will find within the stope design that was optimized for that realization, right? Because again, to form a stope, how the grades are connected is highly important. So essentially, if you have a scenario that you have a lot of high grades, but they are disconnected, you not form any stope there.
Yeah.
Right? So that's how the selectivity of that we have, this higher selectivity that we have in underground mining methods. I think a stochastic approach plays a very important role, right? And the challenge right now is that we have many mining methods, and hence we need to have different optimization models with different geotechnical constraints, operational constraints for all these methods. And of course, we would start by the methods that are more widely used, like the stoping methods, and then we would tackle the other ones. That's our vision. But we can already start from somewhere, right, for underground. And I think the very important exercise that is already available for everybody is the risk analysis, right? We can do risk analysis of a fixed stope design, right? You can do risk analysis of the underground production schedule, right? You can do okay, you want to see ranges of your development network. You can do stope optimization for different realizations to see how would be the extent of the stoping areas in that level. So these are already things that are available. As soon as the simulations are available, mine planners can play a lot, even in the absence of a current stochastic approach, right? But potential, there is a lot. I also think that the risk analysis can support a lot of the underground mine planners to define mining methods, because again, since there is this asymmetric relationship between the stope design, the metal content in the resource model, and in the stope design, you can have like a lower selectivity mining method, right, with a higher selectivity mining method, and you can analyze how these two scenarios would perform, right, in terms of ranges, right? So and again, it's not only dependent on the resource model. So you can have your grade tonnage curves that are not very spread, but once you translate that to a stope design inventory, then that range gets wider, because again, it's a matter of connectivity.
Yeah, it's a fascinating topic, I think, because I think firstly, a fundamental thing is that if you took a simulation and you took an estimation, you might end up with two different mining methods being preferred for that deposit, and that is a fundamental issue, right? That maybe if you used kriging, kriging, and you smooth the model, you might prefer a more bulk mining method, whereas the simulations might highlight that there's not the connectivity of the grades that you expect, and you would need to grade control to very, very fine, resolution or whatever that, and things might break up, right? And you might need to choose a even more selective, mining method. So I think there's a immediate application right there, and I think one thing you raised, to looking at the different realizations, and I know we said in open pit that's kind of that would be cheating to do a mine plan on each, but in the underground context, we other than a block cave or a big bulk stoping operation, you're going to go and do grade control again, and the stopes that you design are going to move, and that's the reality. So long as the I guess the resolution or the support of the simulations are reasonably reflective of the likely grade control, really I think all we're trying to estimate in underground is what's the likely tons and grade that I will get from applying this mining method to this to this deposit. Well, and what's the range that I'm likely to get? And on that basis, is it worth, in investing in developing and, doing further drilling? Because in underground, it's even more expensive to do drilling in advance, right? So people make calls on less and less confidence actually than even in a pit, because they just can't afford the drilling at depth. So I think there's some interesting nuance differences on the underground side versus the open pit side from a philosophical or basic principles of.
Yes. So I do agree with you. Like having the visibility of on how the stope would change, looking at all scenarios, does have value for underground, right? The concept behind but in the end of the day, we need to come up with one design, right? For your drifts, for your stopes, for reporting. So the concept behind the scenes for a stochastic underground optimizer would be having a library of many stope shapes generated based on all the simulations. So you can have one stope that was only identified for scenario one, but never for the other scenarios, right? But that scenario is there. But then you evaluate each of this library of possible scenarios. You evaluate also the performance of that stope against all the other simulations. So now the scheduling process would try now to select the scenarios that would select a final stope design and schedule that would minimize the risk of the blended material as well, right? So in this sense, we would like to blend we can blend some stopes with the higher variability with some stopes with the lower variability, probably lower value, but in order to have a schedule that is more reliable, right? So that's the concept behind the potential stochastic underground mining optimizer. Yeah, it's fascinating. We can talk about it for hours and hours.
For a long time. So I mean, maybe we might look to wrap things up and but move on to just some of your thoughts for what the future of stochastic mine planning is. So maybe you could ask what some of the things that you're like. What are you working on now? Like what's in the things that you're looking to develop in the near term? And
okay, so in the near term, we want to integrate other decision variables that are critical for long-term planning, such as capex decisions and like optimizing holistically capex decisions with the scheduling process, as we discussed before, right? How it works today. So would enable to increase the mining fleet, decrease the mining fleet, do some investments in terms of expanding the processing capacity, etc. Right? We also want to tailor more the model for mines that don't follow the traditional open cut mining method, so going towards more stripping mining type of a mining method, so making it more flexible to other mining methods. And because this will open opportunities to tackle other commodities, such as rare earth elements, right? They don't follow deep hard rock method, right? It's more straight mining, but the uncertainty is still there, right? And we're talking about uncertainty of multiple correlated elements, right? So it's not uncertainty of a single element, but many elements that are spatially correlated. So we want to do that. And again, during the mineral resource estimation conference, Ari Jubali from Newman brought it up, right? We need to have stochastic approaches for medium and short term as well, right? And this will be easier to propagate the results downstream all the way to the operation, right? So that's our focus as well, to have methods for medium term and short term, in which other sources of uncertainty become more critical, such as equipment uncertainty, right? So right now we're scheduling not areas, but we're scheduling activities, and the length of these activities, they can be shrinked, right, or extended based on this equipment uncertainty, productivity uncertainty, right? So this we already have prototypes on this front, right? And the idea is to combine geology plus other source of uncertainty to have a medium-term and short-term schedule. Doesn't mean that in our long-term planning today, we cannot account for other sources of uncertainty. So we can integrate uncertainties related to recoveries, to prices, right? As soon as you are confident with a method that can generate a time series, right, of price fluctuations, this can be already used in the software. Because again, we're optimizing things, accounting for the time dimension. So if you have scenarios of showing yearly fluctuations of the price, this can be already integrated. The challenge is we need to be confident that these scenarios or simulation methods for prices are reliable, right? But we have interesting
another can of worms.
Yes, because then it's not talking with the geologists. We need to talk with the financial people, right? Some other engagement.
Small steps.
Yes.
It's a big step.
Yeah,
big.
We really focus on small wins, right?
Yeah. So, and so, is there anything else that's that where you think it might go? Is there, how do you think it will interact with other technologies? Does AI play a part? Does, where is there anything else you're seeing there in the broad future?
Okay, yeah. So in the future, I think we're gonna have more and more real-time updates of this schedule, right? So now we can update the simulations, not now. Ideally, we would be able to update simulations in the schedules based on sensor data, right? Based on grade control data, and do that in a more real-time manner, right? So this would be the ideal ecosystem, right? We do have like research going towards this direction. Does require a lot of work to be done to make it as a commercial and available technology, but we're getting there. The speed that things are evolving is very motivating.
Yeah, it makes it a lot more possible. It'd be interesting to revisit in 10 years and see if you're correct, and it'll be on the podcast. So that's great.
We're gonna be talking no. Those methods that we talked 10 years ago, no, we have many other much better today. It could happen, no?
No, yeah, absolutely. So look, thank you so much for your time. It's been a really interesting conversation for me, and hopefully for everybody listening. And yeah, I'm interested to see how it all goes, and gets adopted in the industry. I think it's just something that people need to be educated better about, and the more of these types of discussions that we all have, I think hopefully that takes a step towards that. So
Thank you so much, Tarrant. It was a great talk. I hope you enjoyed, and I hope the audience will enjoy as well. Thank you so much for the opportunity. Looking forward to
thanks.
working closer with you and team.
Thanks for joining us on this episode of Fresh Thinking by Snowden Optiro. I hope you really enjoyed the discussion that we had with Matheus, and please reach out to us with your thoughts on what we discussed. If you like the podcast, please subscribe to us, YouTube or any other podcast platform, and we look forward to seeing you again on Fresh Thinking by Snowden Optiro.